Mostly, I would like to thank the organizers for this very nice conference and for inviting me. It's a pleasure to be here. This is actually my first time to be in India, and so far has been really nice, and it's like way beyond what I had expected coming here. Yeah, so thank you very much for the conference. Today, I would like to give maybe an oversimplified talk with the goal is to give an overview of the field that I have been working on in the last 10 years. What is random polynomials? And in the audience, there are people who are, who are expert in the field, like Krishnapur, and I will also want to talk about anti-concentration, which is something that, I know a lot of the work on random matrices that some of the previous talk have been talking, would have some intersection with this. So again, the goal is to give a broad overview of the field and some basic ideas of the methods of anti-concentration that we use in our papers. So let me start off with introducing random polynomials where they show up. So here are some examples. Many of them come from mathematical physics. For instance, in the study of semi-classical approximations for multidimensional quantum systems, and in a work by Sher and Machamda in 2007, they illustrate the link between the real roots the real roots of random polynomials with this diffusion equation with random initial conditions. In a very beautiful work by Dembo and Mukherjee in 2015, they study the probability that random polynomials have no real roots, and that corresponds to a random process, always positive or always negative on the real line. That corresponds to the persistent probabilities of physical systems. Work by, for instance, Werdert and Wigman 2016 study random eigenfunction, what is very closely connected with number theory. And let me take an example. What is so let's say we want to model physical phenomena by point process, and the physical phenomenon that we want to study is, for instance, we have light charge particles that are confined by an external field. This is also known as one component plasma. And so one of the basic properties of this system is that it has the anti-clumping, also known as the repulsion behavior. So the zero set of random polynomials is a natural candidate for this point process with the repulsion. If you remember, actually yesterday, Subro also mentioned another class of point processes that has the repulsion property, what is the determinantal point processes. So random polynomials actually intersect with that class of point processes. And again, could be a natural model for this phenomenon. So what is random polynomial? This is can be written, a random polynomial is something that looks like this. So it is a sum of C0, P0x up to Cn, Pnx, where n is a large number going to infinity. the PI, the little PI are deterministic functions, and the CI are independent random variables with rescale so that it has variance 1. And that is where the randomness comes from. Now, so what are the little PIs? So these are natural basics of the set of functions. So there are 3 main basics that we usually use, right? So the first is when the PIs are simply the monomials. So AIX to the I. So that gives you the so-called random algebraic polynomials. And the second kind of basics is when the PIs are the sine and cosine function. So we come up with Pn is the sum of Ci cosine Ix and Ci sine Ix. And it is called random trigonometric polynomials, or also known as random Fourier series. Another kind of random polynomials, what is more general, is when the PIs form an orthonormal system with respect to a given measure mu on the complex plane. So what are the questions that people study in, when it comes to random polynomials? There are many questions that we can ask. So for instance, what is the density of the complex roots? As studied by Ofer Zeitouni, Riddhipratim, and so on. Now, more generally, there are other questions about the distribution of complex roots. Now, when it comes to the real roots, the very first question is probably, what is the first moment of the number of real roots? And the second moment, or the variance, concentration of the number of real roots. And as we mentioned before, the probability of having no real roots at all. And asymptotic normality, or like central limit theorem for linear statistics of the roots. Now, let me take the first example, what is perhaps the most simplest looking random polynomials. And this is also one of the most intensively studied model of random polynomial. Is known as the Cox polynomial. And it is just a combination of the monomials, so C0 plus C1x plus up to Cnxn, where the CIs can be any random variables with, let's say, mean 0, variance 1. And here are two, so I mentioned two examples that we can keep in mind for this talk is when the CI are plus minus 1 with equal probability. So the CIs are the Rademacher curve, meaning we have a polynomial where the coefficients are just the random sign. You just throw a random sign and then you ask various questions about the number of real roots, or the case when the CIs are standard Gaussian. Now the question, for instance, now what is the expected number of real roots of such polynomials? And here is a simulation of the Cox polynomial of degree 1,000 with Rademacher coefficients. You see most of the root roots actually stay very near the unit circle. Indeed, the limiting distribution of the complex root is uniform on the unit circle, but still there are real roots. Now, so how to calculate the expected number of real roots? This is the very first approach that gives a precise estimate on the expected number of real roots. So here is the starting point. What is a simple observation for a polynomial Pn that doesn't have like a double root, then the number of real roots is given by this formula. It's the limit as delta go to 0, 1 over 2 delta, the integral of absolute value of the derivative on the domain when the function is smaller than delta in absolute value. Now, and here is in the picture is how to see it. So the function is, I draw it as the function f. So let's say f doesn't have a double root and it has a root at x0. So because it doesn't have a double root, it means that, f prime at x0 is non-zero, and so it's either greater than 0 or smaller than 0. In this picture, I draw it as greater than 0. So it's increasing in a small neighborhood around x0. So when delta is sufficiently small, there should be 2 points C and D, around x0, such that FC is negative delta and FD is plus delta. Now, the integration that we see in the box on the neighborhood of x0 will become just the integral from C to D of the derivative of absolute value derivative, which in this case is non-negative. So will be integration of f prime, which is fd minus fc, and that is 2 delta. So that's explain why when we divide by 1/2 delta, we count 1 root. So that is the proof of the CAC, this observation. And from here, if we take the expectation and assume everything is nice, we can bring the expectation inside. So that gives us this formula, which is nowadays known as the characterized formula. So they say that expectation of number of real roots, what is denoted by NN here, is a double integral absolute value of y. So y is in place of the derivative, and rho t 0y dy dt. Here, rho t is the Thorne density of Pn t and Pn prime t. Of course, the Thorne density has most manageable when the random variables are Gaussian, because we can write it in an explicit form. And so this is oftentimes, all of the examples I have seen so far is the most manageable when the random variables are Gaussian. So when the random variable Ci is a Gaussian, this is the one of the first things that one would try. And so, but then the big drawback of the characterized formula would be like what to do when we have like non-Gaussian random variables. Then here is the second approach that was introduced by Ederson Ofer back in 1956, and later refined and improved by a series of papers. And the basic idea is that if you are, suppose you're interested in the number of real roots in an interval from A to B, what you would do is you decompose it into small intervals, I1 up to IK, and you divide them so small that you would expect in each interval 0 or 1 root. And so, okay, so if the polynomial is expected to only have 0 or 1 root in an interval, whether it has 0 or 1 depends on whether you have a sign change at the endpoint. So the number of, so the n ij is the number of roots in the interval ij should be roughly the same as n star ij, where n star ij is whether there is a sign change. Now, how does it help us? It helps because in order to calculate the sign change, the sign of a number, we can use derivative formula, which say that sign of a number x is 1/pi integration on r of sine tx over t dt. Now, so plugging that in, if you have a small interval from x to y, and you want to see whether there is a sign change from Pnx to Pny, plug-in derivative formula would give us this form. And now let's say we want to take expectation. We bring the expectation up to the product of the sign. Now, product of sign is difference of cosine. And so that integration of cosine that corresponds to the real part of the characteristic function. So we reduce it to a double integral of of characteristic functions. And it is nice because we know the characteristic functions of any random variables is something that we can, have some estimate. It is always continuous. So we can do something about it, that is more continuous than what we would get when we use characterized formula when the random variables are non-Gaussian. And so what is the trade-off for this approach? The trade-off is that the very first step is to pass from the number of real roots to the number of sign changes. And that is usually a technically dedicated task, delicate task. And the integration of characteristic function is also not easy either. Usually assume that the random variables have to be IID so that we can control the characteristic function altogether. And usually assume we need to assume, in the setting when the polynomials, the little PIs are sufficiently nice. For instance, we have the cast polynomial. It would work for this method, meaning when the coefficients are just, we have the CAC polynomials when it's just a sum of CI x to the I. It will work because it's still pretty nice. But let's say instead of all the ones here, we change it a little bit to 1.1 or 1.2, something like this, then it would become very hard to estimate, to do the integration. So in other words, doing the integration of the characteristic function is not always robust to the changes. There is a more robust method that has been developed recently. It's known as the universality approach, and it consists of two steps. The first step is to reduce to the case when the random variables are Gaussian, and the coefficients AI here, if there are, being nice. And the second step is to answer whatever question you have for the Gaussian case and nice coefficient. Now this universality approach is actually was introduced before in a series of work by Tao and Wu in random matrix theory, and was later much developed by many researchers. And then Tao and Wu introduced it in the field of random polynomials and later refined. So I want to briefly introduce to people who haven't seen it before what local universality is. So basically it says this. So you have a random polynomial, Pn. It has the roots being zeta1 up to zeta n. And let's say you're interested in this statistic, the sum of f zeta I for some function f. For instance, f is the indicator of a ball. So that will calculate the number of roots inside a ball, center z and radius r. Of course, you can take f to be an indicator of an interval, then that will calculate the expected number of roots inside that interval. Now, so that is the quantity that you would be interested in, for instance. Then local universality says this. Let's say your Pn has this form, the sum of Ci Pix, and where Ci's are general random variables, for instance, plus minus 1. Now, you would compare it with the Gaussian, what is Pn tutor, where the Ci is now replaced by the Ci tutor, which are Gaussian. Now, local universality would say something like this. Under general conditions, one would expect that the expected value of the statistic for Pn would be not too far away from the statistic for the Gaussian case. So that's generally what local universality would mean. And in a paper by myself with Van Vu, we give a set of sufficient conditions for universality to hold on a ball. And there are several conditions, but it boils down to two basic conditions that one need to check. The first is this localization, and this is basically from the CLT. The same idea as the CLT, meaning if we want to, if we expect to have universality, each component PIX should contribute only a little bit to the sum. And the second is the anti-concentration. So we would not want Pn to be too small on the ball that you are, interested in, relatively to the variance, to the standard deviation of Pn. And so, for instance, we would want to have an estimate like this. So we want to control the probability that Pnx0 is very small, smaller than e to the minus n to the power c, where c is a small constant, times the standard deviation of Pnx0. And we want that probability to be small, like smaller than n to the negative 100. So for the rest of the talk, I would like to concentrate on the second part, what is anti-concentration. So in this, it looks like a tool, but anti-concentration has shown up in other places like random matrices, combinatorics, and other places in probability as well. So it now becomes an independent object of study. So what would prevent, a polynomial to have a high anti-concentration probability? So what, meaning, in other words, in what case the polynomial can be very concentrated at a point. So for instance, if we look at the Cauchy polynomial at 1, so, and we look at 1 because most of the positive roots of the Cauchy would, be around 1. So 1 would be, one is the most important point that we would look at when we study local universality of the Cauchy polynomial. And so Pn1 is just the sum of Ci. And let's say here the Ci's are just plus and minus 1. Now the variance of Pn1 is n plus 1. And the probability that Pn1 is precisely 0 is the same as when, out of the n plus 1 random variable Ci, half of them are 1, half of them are negative 1. So that probability becomes n plus 1 choose n plus 1 over 2. So that's to choose the positions of the 1 and the positions of the negative 1 times the probability of each choice of the positions 2 to the minus n minus 1. So that is of order n to the negative 1/2. Now that is too big for our purpose. We would want to have something like n to the negative 100, for instance. So that is too big. And so, okay, so this is a bad case for anti-concentration. And why, where did that come from? That is bad because here all of the coefficients attached to the Ci's are all 1. So we see here when they're all equal, they have a small anti-concentration probability, which is not what we want yet. Okay, so, and here is another example. When AI's are all I, meaning our polynomial will be, let's say Pnx is the sum, AI equals I here, Ci, x to the I. And again, the roots will, the positive roots will concentrate near 1. And so we again look at the point 1. Pn1 is the sum of AICI, and again assume that the CI's are plus minus 1, then we have the sum of plus minus AI. Now this is a random variable, would mean 0. Standard deviation is of order n to the 3/2. Now, within the range of 1 standard deviation, meaning from negative 3/2 to n to the 3/2 to n to the 3/2, we know that S only takes integer values because the AI are integers. So the probability that S is a random variable that with standard deviation from into the 3/2. The S will be something like this. And so the probability that S stay at 0 is at least into the negative 3/2 in order. So again, this is an example when we have a small anti-concentration probability that conflicts with what we would need to prove local universality. And so the general observation here is that if the AIs form an arithmetic progression, then the sum AI-CI would have a small anti-concentration probability. And Halas generalized this observation to the so-called Halas inequality. It says that if you have, if you look at the sum of AI, here epsilon I, but I wrote, CI, but I wrote epsilon I to emphasize that this is for the plus minus 1 random variables. So if any combination of AI, so if you have, let's say, if you want the error term to be n to the negative 100, if any combination of 200 AIs is always larger than some constant A, then the anti-concentration probability will be good. Will be smaller than n to the negative 100. In other words, it's like if the AI doesn't have, don't have an arithmetic progression, an arithmetic structure there, then we would have a good anti-concentration probability. So we used Halas inequality to our problem. So firstly, we would not need the first reduction that we have, which was a major reduction, was that we only need to show that, okay, the polynomial doesn't have to be small at every point, but we only need to show that there exists a point, meaning let's say we're interested in some, local universality around x0, we only need to show that with high probability, we can always find an x1 near x0 such that the anti-concentration probability around x1 is good. And so again, what is P and x1? That is the sum of Ci little pi x1. Now, by Halas inequality, in order to show that x1 is this, we just need to show that, okay, there exists some xi such that for any multiset of total size less than 200, the combination is large at x1. Okay, and okay, so that brings us to the task of finding x1. There is no probability here anymore, so that just there's no CI anymore, no randomness anymore, just a deterministic statement. And so that brings us to the so-called Ramesh inequality that says that given a low degree polynomial of degree d, then the maximum value of q, the polynomial q, on an interval. Right, so it says this. So you have a polynomial q of low degree d, and you have an interval I. Suppose that on I, you know that maximum value of q is large, then the set of points on I on which the polynomial q is small, now that set should be small. So that's the Ramesh inequality. Now applying Ramesh inequality to the q that are a combination of 200 polynomials, then the set of point x1 on which qx1 is small, now that set should be small, ideally small. Now, if that is the case, then we would be able to, do a union bound on all the choices for Q, and then show that there exists some X1 that lies outside of all of the E. And so when is it that we can have, we can apply the Ramanujan inequality and get what we want? Firstly, we would need the D to be, small, like a low degree. And so, for instance, D is a small power of n would be enough. So let's say if we can do it for n, for D equals n to the, some C over 4, for instance, if the contribution, okay, so we want that D to be, even though small, the contribution from the polynomials coming from those D's is already significant, then it would be nice. So if we have, in other words, if we have the sum of pj squared, when j is smaller than our D, if that is a significant contribution to the total variance, then it would be give us, would allow us to actually use Ramanujan inequality in a meaningful way. And so we show that it actually works for a lot of models of random polynomials, including the Cast polynomial and random orthogonal polynomials when the measure is completely supported on the real line. Now, however, so we were thinking that that method would work, was quite happy about it and thought it would work for, because it worked for all the models we have seen until we met with random orthogonal polynomials with exponential weights and turned out to be, it doesn't work anymore. So what are random polynomials, with our measure with exponential weights that correspond to the Hermite measure, like d mu equals e to the minus x squared dx, or more generally the Freud way, d mu equals e to the minus c x to lambda dx. So why is it that it doesn't work anymore? It's because that if we look at the variance, the total variance, the sum of pi squared, now that is of order e to the power n. Now, if we restrict to the low degree ones, so the sum up to n to the power, c, that is actually only e to the n to the power c. Now that is too small compared to e to the power n. So the method doesn't work anymore. However, we managed to find a different way to prove anti-concentration, which I would like to discuss next. So what is the strategy? Going back to the so-called inverse Littlewood-Offord theory that was developed by a series of work by Tao and Vu, Oanh Nguyen and Vu, and some other works that says basically the basic idea were what we were discussing previously, that if the anti-concentration probability is bad, meaning if it is big, then the individual polynomials pkx should have some arithmetic structure. Now, what are our pk? These pk's are orthonormal polynomials. They have their own structure already. For instance, the structure that we focus on is the three-term recurrent, meaning there are coefficients an, bn, such that when we combine them, they satisfy this recurrence. So this structure actually doesn't go well with the arithmetic structure. So we try to show that, okay, these don't go together. And so that will allow us to show that there must be some x in our interval such that it has a good anti-concentration probability. Okay, so now let me go into a little bit of detail. Okay, so from inverse Littlewood-Orford theory, we would know that there is some coefficient Cij such that when we combine big O1 terms of Cij, Pijx, now that would be small, meaning it has some arithmetic structure there. Now we have the three-term recurrence. Now, three-term recurrence basically said that we can write Pn plus 1 in terms of Pm and Pm minus 1. So, of these Pij, we can always reduce to the smallest index, the smallest two indices. So we would reduce from here, be able to go down to some an equation that we call two-term degeneracy, and it's basically says that we would be able to find some m such that Pm is roughly about the same as Pm minus 1 with some correction gamma, where gamma is a low degree polynomial, fractional polynomial. And where do we go from here? We would apply, so this two-term degeneracy together with, we run this sort of the same idea again, meaning we would have, starting from this sum being small, so starting from this sum being small, and we know, if we know that each Pij here is can be written as a low degree polynomial, some low degree polynomial times some fixed Pm and x, then all of these can be written as just a combination of some gamma ij and some Pm. We would have to find a common m for all of them, x, to be very small. Now, so that reduced to now that we call it a one-term degeneracy. So this is very small. Okay, now what happens is that this, we know that this Pmx usually, if we choose m to be sufficiently nice, then Pmx should be sufficiently big compared to the standard deviation. So that reduced to, actually we have a low degree fractional polynomial that is small on the entire interval, what is we show to be impossible. Yeah, so that's basically the idea of the proof. Are there any questions concerning this? If not, then I would like to conclude with an application. So using the framework of local universality, we were able to show that if the measure mu is a measure on R with exponential weights, meaning d mu is e to the minus q dx, where q is, for instance, q is x squared or x to the power lambda, or we actually consider a wide class of exponential weights here, and we show that two things. Firstly, the normalized zero counting measure tau n, which is also known as the empirical measure, converges to some equilibrium measure, mu q, in the weak star topology with probability 1. So that is for, the global universality. Now at the local scale, we show that for any interval AB on the real line, the expected number of roots, sorry, the n star here is, there should be no star here. The number of roots inside the interval AB is approximately 1 over square root 3 of mu q on the interval AB. So we have, and if we take a look at the number of real roots, the total number of real roots, it will be of order n over square root 3. Yeah. So I guess I can only end my talk here. Thank you very much, everyone, for your attention.
We have good enough time to take questions. So I was just wondering whether it is so in your local universality result, whether is it an interesting question to have a quantitative bound on the discrepancy of these two expectations? So like, yeah.
Yeah, so that's a great question. So local universality always require to have a quantitative bound. Sorry, here. Yeah. So always have to have a quantitative bound so that we can say meaningful things.
Okay.
Yeah, just a question also related to this slide. So when would you expect local universality to hold? Like, do you conjecture that it holds more generally than the frameworks you showed, or?
So again, it boils down to if we are in the setting where, so the first setting is usually the case, meaning each individual PI contribute only a little bit to the standard deviation. And so I guess your question is when we would expect to have anti-concentration?
Yeah.
That's a great question. I would say in most cases, we would always expect anti-concentration to hold. It's just that sometimes it's more complicated to establish. Yeah, I also know there are models that I have no idea how to prove anti-concentration, even though with the approaches that we have developed, we work for the models that are the popular models, but I know there are models that are not very popular, and I haven't worked on them very too seriously, but it seems like that the method that we have developed don't work on those models.
But do you think these conditions are necessary, or do you expect also some others not to show local universality, but not to?
The localization should be a must, just like the central limit theorem. Central limit theorem is just a very basic form of local universality, meaning we switched from random variables, general random variables, to Gaussian, and it still converged to the Gaussian. So this more or less another form of central limit theorem. So the localization is a must. Now, anti-concentration, I think it must be, I don't know, maybe, I don't know if people would be able to reduce to, the probability of anti-concentration instead of n to the negative 100, say, to n to the negative 1/2, for instance. Now, if they would be able to, meaning show that with the anti-concentration or probability n to negative 1/2 is already enough to prove local universality. If people can prove that, then it would be fantastic. It would be a lot easier to prove, if the error term is only like n to the negative 1/2, for instance. That would be quite easy.
Okay, thank you.